So what I work on is direct imaging of exoplanets, and this is kind of my keynote image to show everyone tonight. You may have seen this in the last few weeks. Just kind of it's been circulating around. This is the first image of an exoplanet with the James Webb Space Telescope. So this is the exoplanet here, especially these two images were taken at wavelengths where we've never ever been able to take a picture of exoplanets before. So I'm a specialist in detecting and characterizing exoplanets. We have a whole bunch of many different kinds of exoplanets that we know of these days. We have some that are like the gas giants in our own solar system, some that are rocky and terrestrial like our own, some that are like Neptune or like Uranus, but in many cases a lot closer to their star. We also have these super Earth planets, which are completely different from anything we see in our own solar system. Most of these planets, we now have like 5,000 detected. Most have been detected indirectly by their impact on the star that they're orbiting. But what I work on in particular is trying to take pictures of planets. So I'm looking at the biggest and brightest planets. So in other words, gas giants. So direct imaging, when we try to do this, it's kind of like trying to take a picture of a firefly next to a lighthouse. If you want to try to understand the difference in contrast between a planet and the star is orbiting. But it's not that you're looking at the lighthouse from the beach. In this model, if we're here in Edinburgh, our lighthouse is in Dublin. So that is a sort of contrast and resolution that you need. But we have multiple images of exoplanets. So there are stars here, but they've been removed, both with a variety of hardware, but also with a lot of post-processing techniques. And these are what these planets look like. We're seeing these in infrared wavelengths. So that's the sort of wavelengths that the James Webb Space Telescope works at, because they're young and they've just formed, and they're a lot hotter than planets in our solar system. Hence, they're still glowing with their own intrinsic light, and they're bright in the infrared. So these are some of the previous ground-based ones. And JWST is going to be excellent for characterizing these planets. So this is, actually, I've already shown you this planet. I've shown you the JWST image of it. This is the original discovery image from the ground. This planet is like Jupiter, but it's a young version. It's only 14 million years old. Of course, that's only young in terms of astronomy. No one else says 14 million years old is young. And it's more massive. It's about 6 to 8 times more massive than Jupiter. Now, the thing is, I showed you this nice picture already. Getting there from what we get from the telescope is actually fairly complicated. So this is after a lot of post-processing, as mentioned. Here on the left is what the light looks like when we get it straight from the telescope, because we're seeing both the star as well as the planet. And here we're using various techniques. I'm just going to zip through this now, and you can ask me about these, to remove the starlight and keep the planet light in and reveal that planet. So we took pictures of the planet from 2.5 microns out to 15.5 microns. So we took 7 images across the entire infrared. And the advantage of this is that we then can understand where light is being emitted from this planet, all the way from basically across all the wavelengths where it's luminous. So I think I'm going to leave it there in terms of just quick intro, but I can answer questions on this. I just kind of wanted to give you an idea of what James Webb is doing already with young giant exoplanets with taking pictures, but there's going to be a lot more exciting results coming down from the telescope very soon as well.
Thank you, Beth. So what I understood from what you said there is that basically James Webb is helping you get a better look at these exoplanets that previously we just couldn't get a decent image of them because they were kind of in the shadow of these stars, if you like.
Yeah, they're hard to image because they're basically drowned out by all the light from their stars. Mm-hmm. We've done some of this from the ground, but only at limited ranges of wavelengths. Mm-hmm. What JWST does is open up a much wider range of wavelengths, much further out into the infrared, that we can image and characterize these planets.
Mm-hmm. Mm-hmm. Amazing. You must be quite excited about the potential of that.
It is really exciting. Like, so the image I showed for the images at 11 microns and 15 microns, that's the first image of any planet outside of our own solar system at those wavelengths.
Mm-hmm, mm-hmm. Wow, spectacular. Okay, I'm hoping we'll have lots of questions for you about that and many other things. Thank you. Callum, would you like to share your slides with us now if you're able to, please?
Yep. Um, can you see my slides?
Yes.
Okay, so the work that I do is looking at very distant galaxies. So I'm showing here basically a timeline of the universe. And so along the bottom we can see the just in years, and along the top something called redshift. So we think that the universe is about 13.8 billion years old, and we and over that time, galaxies have evolved to form all of the interesting structures that we see when we look at galaxies in the night sky. We see these spirals and ellipticals. But if we trace the clock back to earlier and earlier times, we see that the structure, is not yet formed, and we go back far enough, we'll get to a point where there were no stars in the universe, or we just had neutral gas. So this is kind of the era that I try to understand, and where JWST is really useful for understanding. So we think sort of somewhere in the first billion years or so, that after the Big Bang, we've got this sea of neutral hydrogen gas in this dark universe, where there's no starlight yet, and over time gravity sort of pulls in this gas and eventually condenses and forms stars. And so this point sometimes is referred to as cosmic dawn, and this is kind of the holy grail of this field of research. When did the first stars form in the universe and start this cycle of evolution that leads to the galaxies that we see today, including the galaxy in which our own sun is part of. And I mentioned this quantity redshift, that this is how we measure it, because of the expansion of the universe. The further away galaxies are, the redder they appear. Their light is essentially stretched to redder and redder wavelengths because they appear as if they're moving away from us. And this is due to the expansion of the universe. And so with the Hubble Space Telescope, we were able to do this and push out to about redshift 10, 11-ish. And this is kind of this hard technical limit that the telescope had, where we run out of wavelength, basically. The galaxies were redshifted too far, where we basically run out of flux to be able to see them. And this is because all of the blue light that comes from the galaxy is absorbed by this intervening neutral hydrogen that has not yet been ionized by galaxies. So essentially Hubble had this limit of redshift 11 or so, where we couldn't see galaxies beyond that. And then with JWST, we now can see out to 20, 30 microns to reasonable sensitivity, where we can do this sort of work. And there's kind of two main advantages of JWST here. One is the extended wavelength coverage, and the other is the bigger mirror. We can see fainter stuff, basically. And these two things combined allow us to really open up this whole new era of time in the early universe in which we can see galaxies. And so in July, we kind of analysed all of this early data that came in to look for as many of these most distant galaxies that we could find. And I've highlighted here on this plot, which we think is currently the furthest identified candidate, which is at redshift 16 or so. And so I'll just, this is another image to kind of illustrate how we search for them. It's slightly more technical, but as you can see, this is what, as a function of wavelength, a galaxy spectrum would look like. And this illustrates the idea that you see it in redder wavelengths, but you don't see it in the bluer wavelengths. And so it appears to look like something like this through the different filters, where we see nothing in the shorter wavelengths, and then we start to see this object in the longer wavelengths. And this is this object here that we kind of got excited about when we discovered it in late July, with this redshift of 16, which corresponds to about 250 million years after the Big Bang. Again, that sounds like a long time, but in the context of 13.8 billion years of the universe, this is a very early time to be seeing a galaxy. As you can see, it looks like a faint red blob, but this is kind of very exciting to be able to see such an early galaxy. This is earlier than many of us expected to be able to see something, and to be able to see a galaxy this distant, this early, really surprised us and shows us that maybe there is a more abundance of these distant galaxies in the early universe than we originally suspected, and that galaxy formation started earlier than was perhaps assumed before, when we just had Hubble to to see out to about redshift 11 or so. So this is kind of summarizes generally the work that I've been doing with the James Webb Space Telescope, which is trying to search for these the most distant galaxies in the universe.
That's incredible. Thank you, Callum, for that pit stop tour. It's amazing to me to hear you say that you found a galaxy that's so old. I mean, that's just astonishing. And I wonder if you could just quickly say a word or two about what your expectations were based on what we understood from Hubble, like how instead of 250 million, what might we have expected to see?
Yeah, so there were sort of various different models going into this where people had, using supercomputers, they'd done these simulations to say, based on this amount of observing time with JWST, how many galaxies in this area on the sky could we expect to see at this time? And with this early data, people said maybe we could see something out, maybe we'd get one galaxy or so around redshift 13, which is about sort of 350 million years after the Big Bang.
Right.
So we're getting smaller and smaller incremental times as we go push further and further back. But to see something so, it was almost too easy to find this galaxy. It was,
Really.
In this early data, which is not going to be as good as some of the data that we're going to get very shortly, which is going to be much better quality. And, it's really exciting that we might be able to find loads more of these galaxies that are seemingly further than we thought we would find this early on.
Oh, it sounds like it's going to be keeping you busy for a while. Yes. Excellent. Thank you both very much. What a fascinating contrast between your two areas of research as well. Really interesting. And I can see some questions appearing in the chat already. So I'll just kick off with this one. Helen Marshall is asking, question for both of you. Given how old some of the galaxies in the universe are, do you think there's other life out there? Do you think we'll ever know in our lifetimes if there's other life out there? I guess you get asked this from time to time.
Just a bit, yes. Who wants to start?
I mean, I could talk a little bit about sort of the large scale structure of the universe and just the large number of galaxies that we know exist in the universe. And if we think about it statistically, it's hard to constrain because we don't quite know exactly what conditions are required for life, like what range of conditions would allow life to evolve. But if we think about the sheer number of galaxies in the universe, billions and billions of them, and how many stars they contain billions of stars, and we know now that most stars have a planet around them, then the probability seems quite high that there would be some sort of life outside the universe. And Beth can maybe talk more about the planet.
Okay, so now I'll zoom into somewhat closer distance scales. So in our own galaxy, we already have billions of stars. And again, we do expect many of them to have planets. Now we have a huge diversity of planets, from ones that are roasting to ones that are frigid, but we definitely have discovered planets in the habitable zone around their stars already. We don't actually know if they're inhabited, but they don't seem uncommon. We are not actually right now particularly sensitive to planets like our own, around stars like our own. Most of the habitable zone planets we know of are around smaller, redder stars. And JWST actually will, for just a very handful of these planets around small red stars, be able to search for signs of life. So that will be a really interesting result. I mean, I'm talking literally 3 or 4 planets over the course of the lifetime of JWST that will be amenable to this sort of search. And what they'll be looking for is a combination of molecules that you shouldn't have if the atmosphere is in equilibrium. So you shouldn't have like methane and CO and ozone if they're in equilibrium. And so if you did find a planet that had all 3, that would be an indication that it might have life that's driving that non-equilibrium. Now, again, it's just going to be a very small number of planets that JWST can do that for, and for a lot of observing time. I do think that in the next couple of decades, when telescopes like the extremely large telescopes and the successors, the space-based successors to JWST come online, that we have a good shot of finding signs of life on another planet. But it's most likely going to be like, oh, maybe there's some microbes there. It's much less likely to be a clear message from another civilization.
Yeah, an intelligent life form, that we might expect from watching the movies for example.
Yeah.
I wonder why you think there's such a small number of planets that might be amenable to that kind of analysis, Beth?
Okay, so part of it is just the ones that are, there's two things going on. There's the habitable zone planets that we can detect with current instruments, which are these planets around these very low mass stars. We detect them via a technique called exoplanet transits. So if they pass in front of their star, you'll see the light of the star drop just a little bit. And because they're around small stars, they're easier to detect. They're also, because they're around stars that aren't putting a lot of energy out, they have to be much closer to their star to get enough energy to have liquid water and be potentially habitable, which means that their orbital periods are quite small, which means that if you're looking for them passing in front, you can see that happen relatively frequently.
Okay.
So they're easier to detect. Then it's essentially that we only have a handful of those. The ones that are more like our own Earth, we're going to require future telescopes and instruments to detect.
Okay, thank you both. That was actually very enlightening. I guess it's one of these conversations that comes up from time to time, but it's great to have an informed view. So thank you. We have another question in the chat. Leslie Garton has asked, does the discovery of earlier than expected galaxy formation have any correlation at all to whether or not the value of the Hubble constant will change? Callum, maybe that's one for you. Maybe you could explain for some of us what the Hubble constant is.
Yeah, so the Hubble constant is essentially the sort of measurement of locally how the universe is expanding. I say locally, not sort of because we think with the discovery of something called dark energy that the expansion rate of the universe is changing with time. But the Hubble constant has been sort of the subject of a lot of attention in the past decade or so, because there's this tension between different methods of trying to constrain dark energy, for example, in what they measure the Hubble constant. So one technique is measuring distant supernovae, and another, for example, is looking at the cosmic microwave background, which is this afterglow of the Big Bang, and they have this sort of tension where they find different values. So it's kind of been a focus of a lot of attention. With sort of galaxy formation happening earlier, it doesn't really have any bearing on the Hubble constant so much, although there has been a bit of discussion on whether this is consistent with the standard model of cosmology, which we call lambda CDM. So the lambda standing for the constant that Einstein came up with that has now become to represent dark energy, and then CDM standing for cold dark matter. So this is basically just our understanding of dark matter. And this is kind of a general model that describes cosmology. Now, the sort of question that's been raised here is there basically enough time in the universe and enough baryons to form stars? Is there enough stuff basically that can form stars in this time to build a galaxy that we can then see this early on? And there's been a few papers that have come out trying to say that, well, this actually is in tension with this model. This shows this model is wrong because we couldn't have a galaxy this early with lambda CDM. I would argue that this is probably because we've been overestimating the stellar mass of this object. Trying to measure the mass of a distant galaxy is something that's very difficult to do, mainly because we're only able to see, so what we're seeing with JWST is infrared light. But because of this redshift that I mentioned before, what we're actually seeing is light that was emitted in the ultraviolet. And that has been redshifted, that when it reaches us, it's in the infrared. So what we're actually measuring physically of the galaxy is its ultraviolet light, and we can't really constrain the mass of the stars in that galaxy simply based on the ultraviolet, because stars that shine in the ultraviolet are primarily the most massive stars, and most stars are not these massive blue stars that contribute to this light. Most are older, redder stars, and we can't see that. So we can't actually constrain the mass, and I would argue that it's been overestimated in that our current understanding of cosmology and the standard model is probably fine for now. But it is interesting how the discovery of early galaxies could put constraints on or put tension on that model.
Thank you, Callum. What, again, a very comprehensive answer. Leslie, I hope that answers your question. Beth, do you have anything to add to what Callum said?
I definitely do not.
That's very elegant of you to say that. So I think we've got some questions from the ScotSci committee, so I'll just have a look at some of those and maybe put some of those to you. Again, this could be for either or both of you. What will you remember about the emergence of the James Webb Space Telescope? You know, when you look back on this in 10, 5, 20 years' time, what will you remember about the telescope and its kind of early days? And what do you think its legacy will be? And just as a kind of follow up to that, do you think it will have the same impact that Hubble has had and that it's become a household name?
I'll start with the impact side. Yes, absolutely. I think it already is as much a household name as the Hubble Space Telescope. And I think my first impression when we first got some of the data from the James Webb Space Telescope was just being stunned at the quality of the data. So I showed that exoplanet image. The team I'm working with, we also got a spectrum of a more widely separated, less high contrast planetary mass object. And we got a spectrum at quite high resolution, and just the detail in the spectrum. We saw just so many spectral features we'd never seen in one of these objects before. So that I think is going to stick with me.
Mm-hmm, mm-hmm. Thank you, Beth. How about you, Callum? What were your first impressions?
Yeah, I think I agree with that point about just how amazing the data was. I mean, this sort of past year leading up to it, I've been working on ground-based data, trying to look for high redshift galaxies, and going through the pain of trying to find a few high redshift galaxies in this ground-based data compared to having this JWST data, where it was almost just like they were there. It was so easy to find them. That it was, the quality really is amazing, and the fact that we're able to resolve these distant galaxies so well, like many of these, including this redshift 16 galaxy, is resolved. It's not just a point source. We can actually see. We can estimate a size of this galaxy, for example, and we can do that up to the highest redshifts. That's quite unexpected. And as well with spectra as well, we were able to, in a redshift 8 galaxy, so this is around I think maybe 500 million years after the Big Bang or so, we were able to detect these really faint what we call auroral oxygen lines, and we can directly measure the metallicity of the gas in these galaxies. And that was something that was unexpected, that people maybe thought they could do up to, we're going to be able to do with James Webb for maybe around redshift sort of 2, 3, 4. But the fact that we could do this at redshift 8, and this came in the early data release that happened in mid-July, I mean, that was quite a shock, and it shows you just how good quality it was.
Mm-hmm, mm-hmm. Amazing. It sounds like you've both kind of had your expectations exceeded. It goes back to, Callum, the point that you made at the outset when you talked about finding this this really early star. Yeah. Galaxy, sorry. Yeah. I mean, it's really encouraging to hear you say that, and it makes me quite hopeful for what we've yet to hear. What the telescope has yet to discover for us all. It's exciting. I wonder. 2 questions came into my mind as you were talking there, Callum, and I wonder about just if you could talk us through the process by which the data is recovered and processed, because I mean, for me, I kind of have this idea of a telescope just capturing lots of images, and then somehow that turns into information that we can all share and understand. But I don't. It's kind of black smoke and magic for me. So can either of you just talk through, the kind of behind the scenes technical stuff that goes on?
Sure. Okay, so our data required a lot of post-processing. I think I showed the initial image of the star and the planets where you can't see the planet because the star overwhelms it. So our data came in either a set of images, and then we would need to process the images, like model out the star to be able to see the planet. That was the one set of data. The other set of data was a spectrum. But the way the spectrum worked, it's with the type of instrument called an integral field spectrograph, where it essentially just takes images in lots of small wavelength bins. So you have a series of images, and you have to go and extract the light from your object in each of those different wavelength ranges and build up the spectrum that way.
Okay, and can you give us a sense of, how much resource that takes, like how much computing power you need, or how many man hours you would need, for example, to capture something meaningful?
So in terms of computing power for that sort of data processing, we don't have a huge data volume. You could do that on a typical laptop.
Right.
Having the experience and really knowing what to do with it, that's another issue. And a lot of the work of our team has been building algorithms and knowing how to work with that data and figuring out how to calibrate that data.
Mm-hmm, mm-hmm, mm-hmm. Okay, thank you. Callum, do you want to say anything about data science?
So with data processing, I mean, when it comes off the telescope, there's kind of background subtractions and things like that have got to happen. But in terms of this kind of analysis that for finding distant galaxies, it's mainly based on that technique I kind of showed in the opening, where we can see it in the longer wavelength images, and then we can't at the shorter wavelengths. So it's basically searching for things that appear there and then don't appear in the shorter wavelength. And then we fit a set of templates based on theoretical galaxy models, based on the stars and the gas that are in there, to then try to see whether the shape of the spectral energy distribution is what we would expect or not. And then we fit those models, and then we can basically try to determine, as a function of redshift, where is this galaxy most likely to be based on the shape of that.
And again, like, how long would that typically take you or a team of scientists to do?
So yeah, in terms of computing power, it doesn't take that much, especially with the early data, where the amount of area covered is not that big. And it's certainly going to become more of a challenge with some of the bigger surveys that are starting. For example, the Primer survey, this is something that we're leading in Edinburgh, that is going to be one of the widest JWST surveys, and it's going to be 180 hours worth of telescope time, and it's going to cover a large area of the sky, and that's going to be quite a big volume, and that's something that we are kind of trying to prepare for right now. But this early data was fairly small and fairly manageable in it, and we took about 2 weeks or so from getting the data and then working non-stop basically to then submitting the paper.
Okay, thank you. 180 hours, I just wonder. Goodness me, that sounds like quite an undertaking. Leslie has come back to the chat with a second question. Sorry, with a couple of questions. Any comment on the James Webb Space Telescope's imaging of the impact of DART on the asteroid Dimorphos? And would you please explain how an object is actually targeted for imaging? I guess that's a separate question. Are the distances between objects so vast that they don't block fields of view? So maybe we could take the DART question first. Any comment on the imaging of the impact of DART on an asteroid?
I think it was very useful for both HST and JWST to be able to image it during the impact. And certainly you see a lot more, there's ground-based imaging taken at the same time. You see a lot more structure in the JWST image.
And can you please explain how an object is targeted for imaging by the JWST? Are the distances between objects so vast that they don't block fields of view?
I'm not quite sure I understand the question. The objects I'm looking at are mostly what we would refer to as point sources. So they're unresolved. And in general, they're going to, there's not anything so close to it that would block the field of view for JWST when we're observing it.
Can I ask what you mean by unresolved, Beth? I'm not sure that means what I think it means for you.
Okay, so if you look at a star in the sky yourself, it looks like just a small twinkling point of light, although obviously that star is not just a tiny point of light. What's going on is that your eye can't resolve it. It's too small. So that's true with definitely the things I'm looking at. In the case of like a directly imaged exoplanet, we then use the capability of JWST to resolve the planet and the star from each other, but each of them is still just a point of light. We can't actually zoom in enough that we can't like for the planet, we can't like see continents, or we can't map it out. We just see one single point of light.
So resolve in the sense of resolution, in the sense that we talk about high resolution images, it's resolve in that sense.
Yeah.
It's like seeing the detail that's there. Yeah, okay. Gotcha. Thank you. While we're on the subject of images, that was another question I had. I have on as my wallpaper on my computer, I have one of the NASA images that was in the early release back in July. And it's so beautiful, it looks like a painting. The images are, the colours are so contrasting, the details of the stars are so sharp. Like, how are these images created from data? What's the process, and why is it so breathtakingly gorgeous to look at? Does that just say something about us as people, or is there more to it than that?
Yeah, there's a lot of work that goes into those images. And can I share one?
Please.
This may have been the one you were thinking of, or this may have been a different one.
Yes, that's the one I have. Yeah, it's just spectacular.
Which is a very beautiful star forming region. So all of this is gas and dust. And behind it are little stars that are forming, little baby stars that are forming, actually very big baby stars that are forming in the gas and dust. Okay, so first thing is JWST does not work in the same wavelengths that our eyes see. So all of this is false color. This is a 3-color image. So it's taking images in 3 different bands of the infrared and then assigning those images, which would be black and white images, assigning the brightnesses to different wavelengths that we can see with our eyes. So basically translating the pictures from the infrared that we can't see to optical light that we can see. And so that's where you get the color from. It's a false color image. Now, what JWST really does give you is this beautiful resolution. So it is a very sharp image. But a lot of the post-processing, there is a team at the Space Telescope Science Institute in Baltimore who take the raw data, and unlike Callum and me, who are working primarily on science, and our images are maybe not the prettiest, that team is more for producing the public beautiful images and spends a lot of time on the aesthetic of the image.
I see. So I don't know how to say this politely. It's not an artist's impression, is it? It's accurate, but the colours are, perhaps there's a bit of license in which colours are used.
Yeah, so it's assigning colors to different wavelengths that we can't see those wavelengths with our eyes. So the choice and assignment of colors and adjusting everything so it looks attractive and aesthetically pleasing, there's a lot of judgment that goes into that.
What's your take on it? When you look at that, what do you see?
Oh, it's gorgeous. I think the star-forming regions are fascinating. You see all this nebulosity. This is a stellar nursery. So while you're seeing the very pretty picture, this is still a really useful image for scientists. It also shows the power of Webb because you can see, so this cloud of gas and dust, looking in the infrared, we can see through and see these little stars forming in here. If you took an image of the same region with the optical, the clouds of gas and dust would block out the optical light. So you would just see an opaque cloud. You wouldn't be able to see these stars forming inside the cloud. So this is this image really shows the power of Webb and the power of going into the infrared.
I love the idea of a stellar nursery. And do you think we could get another image maybe a bit later on, and we'll see a different, see how those objects develop? Is that a possibility?
So the timescales for those objects are very different than the timescales for our lives.
Okay.
So yes, if you could wait 500,000 years and image this, yes. But on the scale of our lifetime, it's not going to look different.
Okay, it's not going to change much from now for the next wee while. I just need to get my cat off my computer. Excuse me. Yeah, that's amazing. Thank you, Beth, for explaining that to us. So just another question that the committee had was, we read articles about finding the oldest stars, and how do we measure that? And Callum, you talked about this in your presentation. Do you want to say a little bit more about that process and how that kind of is determined?
Yeah, so it's the way we kind of measure this is based on the redshift. And so that is primarily with imaging, which is what we've done so far. What we're doing is, I'll share my screen again actually, because to show this plot. So this is basically flux against wavelength. And what these different coloured things here show are the different filters that we can take images in with JWST. And so we basically take the same patch of sky and we image it with all these different filters. And then this black line here shows a galaxy template. So this is a model of what a galaxy could look like. This is not what we actually see. And so what this, and as this increases in redshift, this basically shifts to the right. And so when we see in the images, what we see is we'll see nothing in this image because there's no light here, nothing here. We'll see a little bit of something here, but it'll be quite faint because it's halfway through. And then we'll see something in this image and so on. And so we can determine what we call a photometric redshift, which is based on where this position of where this break in the flux is. But this is quite uncertain, and the uncertainty is essentially determined by how wide these filters are, because these filters are letting in light from quite a broad wavelength range. And so it doesn't give us a precise estimate of when this galaxy is. And to do that, we need spectroscopy. So this is something that Beth mentioned with exoplanets, but we can also do it with galaxies. We can, and this is where we basically, instead of taking these broad filters, we're getting a much finer resolution as a function of wavelength, and we can see much sort of sharper, fine features as a function of wavelength. And we can measure things that are such as this, which are emission lines. And so these are at very specific wavelengths. You get a lot of light coming through, and this is from different elements that you get in the galaxy. But because of how specific this is, where this position is, we can get a very accurate measurement of the redshift, and we call this a spectroscopic redshift. So ideally, once we've detected these galaxies, we want to then follow up with spectroscopy to confirm that they are at the redshifts that we think they broadly are from the imaging, and that gives us a much more precise measurement. And so, for example, for our redshift 16 galaxy that we found here, we've got some time in December where we're going to get spectroscopy, which was part of this DDT proposal that they do, where if observations are time sensitive, you can apply for time outside of the yearly cycles, so that we can quickly get follow-up to see whether this is actually at the redshift that we are. And we were lucky that we joined with another team that actually were involved in taking the data, and we're going to get some time in December, and so hopefully shortly we will have an answer where we can definitively say what the redshift is to good precision of this galaxy.
That's amazing, and I love the collaboration in that as well, that you just mentioned there. You know, just trying to make the best use of the resource by joining with other teams and using what's available there. Incredible. Can we talk maybe for a couple of minutes about Hubble and what the JWST will mean for Hubble? Does Hubble still, I mean, as we mentioned before, it's a household name. Is it still going to have a place in our hearts? Is there still a purpose for Hubble? And you know, what impact will the James Webb have on Hubble's kind of contribution?
They're actually very complementary. So they work at different wavelengths. Hubble works from the ultraviolet through the optical and a little bit of the infrared. JWST has a little bit of overlap in the infrared, but then goes much further into the infrared than HST. JWST is bigger, which does give us better resolution and better sensitivity in the infrared, but because of the difference in wavelengths, they really complement each other much more than they compete.
Okay, so there's not a question of Hubble being kind of pushed out of the picture by
in terms JWST. Of, I mean, in fact, where it's really unique, it is the only ultraviolet telescope currently working. So
Hubble
if you want to work in the ultraviolet, Hubble is the only option you have right now.
Right. Okay. And this isn't something you spend much time thinking about. What's the kind of lifespan of Hubble? Like, how much longer will we be enjoying those images?
5 to 10 years at least.
Okay, right.
So Hubble right now, I'm actually on the Hubble Space Telescope user committee. And what we've been told mostly is that it comes down to the gyros. Right now, there was originally 4, and we're down to 2 the gyroscopes basically what allowed it to point. And there's still enough working gyroscopes, but even when they get down to 1 gyro, they can keep on working there. So that's going to be the limiting factor, but there's still a lot of good time left in the gyroscopes on Hubble.
Okay, and sorry, can you just explain where the gyroscopes are? Are those like, and kind of how are they when we get down to 1? What will that limit? Will that limit the patch of sky that Hubble can look at? Or?
It will limit pointing accuracy some,
Right.
but the team at Space Telescope, I mean, they basically would understand how to operate it in that mode.
Right, I see. Okay. So, and obviously because Hubble's a space telescope, it's not something we can control. We can't go out there and fit new gyros on it.
Well, we used to be able to when there was a space shuttle. Hubble is in an orbit where you can service it if you have the space vehicle that's capable of servicing it. There's actually now a study to potentially do another servicing mission. So with servicing missions, Hubble can probably keep on going indefinitely, although the chances of another one are pretty small. JWST is at a much further out orbit. There's not the possibility of a servicing mission.
Okay.
So what limits it is the amount of fuel it has to stay in its orbit. When it runs out of fuel, it won't be able to stay in its orbit.
I see. That makes perfect sense. Thank you, Beth. Callum, do you want to add anything to what Beth said there?
Yeah, just to say again, it's very complementary, and in many of the sort of surveys that we're doing with JWST, where we're trying to search for distant galaxies, are being done in the same areas where Hubble was pointed, and that's because we can combine the Hubble data at shorter wavelengths with JWST, because JWST doesn't provide optical data, only in the infrared. So we can do that Hubble with the optical plus infrared with JWST to kind of, and that allows us to study galaxies over all of cosmic time, basically, all the way back to the earliest ones.
Okay, so the Hubble can help your research as well.
Yeah, it works really well with JWST.
Right, so have you been using Hubble data too in your own work?
So far, the kind of early deep fields were in areas where the Hubble data wasn't the best. They were quite shallow observations taken with Hubble, so they didn't see as deep, basically, as JWST did. Basically what that does is it restricts us to the really, really distant high redshift stuff, which is actually where most of the excitement was. So far it's not been that much of a hindrance. A lot of the big surveys that are coming up that we're starting to take data, for example, in recent days, actually yesterday, we just got some new data from the Hubble Ultra Deep Field, perhaps the most famous deep field, and that was the deepest Hubble imaging, where there's so much data, and we've got now JWST data in that field, and that's really exciting, because that we have loads of galaxies there where we can now add on our JWST information, and that'll help reveal more properties about it.
I can see that would be quite a rich seam for you to mine, combining those two sets. While we're on the subject of looking back in time, I wonder if either of you have a thought on the Big Bang. Will we ever get back that far and be able to really understand what took place?
So yeah, with regards to the Big Bang, I mean, with JWST and infrared telescopes, we can only see back so far. But we've actually been able to see further than JWST already with the Planck mission and other missions similar to that, which look at the cosmic microwave background. So this is about 400,000 years after the Big Bang, this light. But this is in a time well before there were stars. And so we have this missing gap, basically, between this cosmic microwave background, which is at a redshift of about 1,000 for redshift context, compared to where we had redshift 11 with Hubble, and we had this big gap. And JWST will be able to push to maybe sort of redshift 20 at the most, but then we still are going to have this gap where, we don't know. And there's other experiments that are going to probe that area that are potentially upcoming. But yeah, I think we're not going to probably be able to see beyond the cosmic microwave background. That's probably the earliest light that we'll ever be able to see.
Right. Ever, regardless of the technology that we have, just because we can't access anything at those wavelengths.
It's mainly because the light before then couldn't escape, because when the universe was so small and hot and condensed, that light was essentially scattering constantly off electrons and protons that were just floating around basically in this hot plasma that was the universe. And we think at around this point of 400,000 years, there was a very rapid expansion again at that point, and that basically freed the photons. They were able to just be able to travel free, unencumbered by being scattered. And then eventually they reach our telescopes, and that's what we call the cosmic microwave background.
Okay, but is it true that, for example, the work that you're doing, looking at as far back as we can in terms of your the spectrum that you're focusing on, will that help us kind of understand the evolution of these early galaxies and perhaps fill in some of the theory, at least, of what went on?
Yeah, so one of the big missing things, and I mentioned earlier the tension about the Hubble constant and our general big picture of the standard model of cosmology, and the key missing ingredient, I think, in all of that is that we don't understand properly how galaxies form and evolve. And getting better insight on galaxy formation and evolution is kind of the missing picture, because we understand on the absolute largest scales broadly how the universe works. We understand, dark matter and dark energy in the sense of on the biggest scales. But as you get to small scales, and this time when I mean small scales, I mean galaxies, which isn't really small scales, but it's smaller than the whole universe. That then there starts to be things that break down in this model. And I think the missing piece in trying to understand cosmology as a whole really is how galaxies form and evolve.
Wow. Beth, anything you want to say about the Big Bang?
I think Callum's already put it very eloquently.
Okay. Just looking back at our questions from the committee. We've seen a range of images from planets to distant stars. Would you be more interested in seeing JWST study objects closer to home or the more distant parts of the universe?
What do you mean by closer to home? I guess solar system?
Yeah, I guess in terms of distance as we understand it.
Yeah. Well, I mean, I suspect that this is just going to come down along the lines of the sort of research that I do versus what Callum does, because I'm thrilled to see how much time with JWST is going to study exoplanets, which are by cosmic standards very close. They're all within maybe 100, 200 light years from us.
Right, okay. Callum, do you want to say any more about that?
Well, yeah, clearly I'm biased towards the more distant things, but certainly do always find the exoplanet results interesting as well. And it's just amazing to see how one telescope can kind of cover all the different scales in astronomy. It's always been something that's kind of interesting because exoplanets and distant galaxies both use infrared observations. So there's sort of been a bit of a history of using similar instruments, even though they are the kind of opposite ends of the distance spectrum.
Maybe just to wrap up then, we can go to each of you in turn and just ask you what you're most excited about that JWST might deliver, perhaps during your career, perhaps, later on, because there's going to be a lot of work, unraveling all the data. Beth, would you like to take that one first?
So right now with JWST, we're imaging baby Jupiters, planets like Jupiter in our own solar system, but a lot hotter because they just formed. JWST gives us the opportunity and the capability to possibly image also baby Neptunes and baby Uranuses. And that I think is particularly exciting. It's just because it's so sensitive at the longer wavelengths, they can push down to lower mass planets that we've never been able to directly image before.
Okay, so Neptune and Uranus, in contrast to Jupiter, would be a smaller large planet. Yeah.
Cooler, a bit fainter.
Sorry, smaller, cooler, and
a bit fainter.
A bit fainter. Okay, in terms of the signal. Okay. And Callum, for you, I guess it's just trying to push the boundaries of going back in time and seeing what's out there.
Yeah, trying to push back to this earliest point when the first stars would have formed. But also, I suppose, with the other instruments on JWST, so the spectroscopy side of things as well, we can now, it's not just a matter of this is the redshift, this is the distance to the galaxy, but actually understanding their properties in more detail. So getting better measurements of their stellar mass, understanding the metallicity of these galaxies. So the production of metals is kind of something I've not really talked about much here, but we expect these early stars, because they formed out of basically pure hydrogen and a little bit of helium. They're these very pure systems where there's no metals, there's nothing heavier than hydrogen and helium, but stars produce these elements very quickly. And so these first stars would have been very large, very bright, very hot, and would have been quite unstable, and would have sort of formed these metals quite quickly, we think, and then thrown them as they die back out into these galaxies. So that's something that's really interesting, is how quickly did metals form and these heavier elements form, because this is kind of the sort of earliest point of a chemical evolution that leads to all of the elements that we see in the universe today that make up the Earth, that make up, you know, everything that we know. They would have all been traced back to this original point in the first stars when they formed. And one thing that JWST will be really useful for is getting more detailed measurements of the metal content of early galaxies and seeing that earliest point of this chemical evolution.
And this is perhaps a silly question, but I'm going to ask it anyway. This insight into, you know, the evolution of the chemical elements, could that be of any help for particle physics in terms of understanding the formation of atoms or subatomic particles?
I'm not so sure.
Right.
With terms of particle physics, this is more, I think, trying to kind of understand the chemistry, I suppose, and I suppose the rate at which these chemicals build up in the early universe. You know, how quickly do we form these elements, and all this. I'm not sure about the crossover with particle physics so much.
Yeah, maybe our physicists working closer to home will be able to focus on those and leave cosmology to you and Beth. I think you've given us an incredible hour of chat. Thank you both very much indeed. Is there anything either of you would like to mention that maybe we've not talked about tonight?
I guess one last thing is, if you're looking for pretty pictures with JWST, it is worth also looking at some of the solar system pictures. There are some really spectacular images of Jupiter and also, I think, of Uranus that have been taken, and definitely worth just Googling those.
Thank you, Beth. That's a great tip. And I'll just mention as well, in case anyone's not aware, that NASA has an incredible image gallery and it's all free to download. So you can spend as much time as you like on NASA's website, helping yourself to their gorgeous pictures. So thank you, Beth. I'll do that. Callum, anything you want to add at a parting note?
Nothing more other than to say just watch out for all of the news that will come in the next few years, and it's an exciting time.
Maybe you can come back and talk to us after December when you've had your data set and you've worked on that.
Yeah, happy to.
Okay. Well, thank you both very much indeed. We couldn't do this without you, and I'm really grateful. It's been fascinating to speak to you both. And thank you very much to everyone who came along and asked questions and took part.